So hello and welcome to CppNow and my talk on embracing noexcept operators and specifiers safely. And I'll just get started. Hopefully this is going to work. There we go. Safely. Okay, so welcome to my talk. My name is John Lakos. I work at Bloomberg in New York City. Been there for over 20 years. I'm an active member of the C++ Standards Committee. If I can untangle my tongue. Originally started there about 2005, have been continuously there and haven't missed a meeting unless it's been virtual since 2007. And I've written a few books. One of them is from 1996. You may remember it. Then there's another one that I just finished during the pandemic, and that's this one. And these are both architecture books. And we're not going to talk about these books here because this is not about software architecture. This is actually the other side of the spectrum where we're talking about detailed language features. And so the next thing I did was set about working with a fellow named Vittorio Romeo. I'm sure you've known him because he's been here since, I don't know what, it started out as a helper, I think, and then became quite a prolific developer and works at Bloomberg today. And we started thinking we would write this book. And it got a little bigger than we thought it was going to be. And in fact, a lot of people got involved in helping us write it. And these are just quick example of some of the people. There's certainly not all of them, but you may recognize some faces in here. And really quite a few. And I'm very grateful to all of them because we could not have done it without the help of tremendous number of people. There's an unbelievable amount of expertise that got jammed into this thing. And so anyway, I'm excited about it. And what I'm going to do today is talk about, give you kind of an introduction to the book and also an introduction to exceptions, exception specifications and the exception noexcept operator. So that's what I'm going to do. And part one, introduction. So I'm going to talk about the book a little bit, then I'm going to talk about the noexcept operator, and then I'm going to talk about the noexcept specifier, and then I'm going to talk about a conclusion, which is going to be very short. So let's get started. Introduction. So here's the book, and what do we mean by safely? So I chose this really to be an interesting word, like levelization. I picked that word. It's an interesting word and it gets people's attention. So anyway, safely can get your hair on your back of your neck up because what do you mean by safely? So we broke the book into 3 chapters and we subjectively chose what we consider to be safe based on our collective experience. And safe means that there's a lot of value in this and there's not much to go wrong. Then there are these conditionally safe features that, yes, they're very powerful and they do great things, but you really do need to be familiar with how they're used and how not to misuse them. And then chapter 3, we say unsafe features. And again, just to make people interested, we say unsafe. There's nothing unsafe about the feature, just like there's nothing unsafe about a gun if it's used in a reasonable way. But guns are more likely to kill people than feathers. And so chapter 3 has the potential to cost a large firm who's very skilled in dealing with earlier generations of C++, start introducing these chapter 3 features into the mix, it could actually be problematic. And that's the thesis of this. So this book was written for large companies, for people who are expert developers who want to become familiar with 11 and 14 and use their same wise wisdom that they've gained over the ages doing what they've done all their lives. So people who are my vintage, this book was designed for them, and this book is designed for me because I learned a whole lot about it by having to produce the book. So that's the idea. And I am by no means an expert on the fancy features of C++ 11, 14, 17, and 20. I'm much more familiar with them than I was when I started, and I'm doing my best to present what I understand the detailed features to be. When it comes to the architectural principles and how they affect a large system, I feel I'm on more sure ground. So proceeding on, The book is broken down into, each chapter of the 3 chapters broken down into an 11 section and a 14 section. So I'm giving you just some examples of what this is all about here. And this is kind of just an idea to give you a feel of what the book like. There are 3 chapters basically. Chapter 0 is what I'm giving you now. And here are the 3 main chapters. And chapter 2 is by far, the lion's share. Chapter 2, section 1 is the lion's share of the book, because that's what most of it is. Anyway, this is the format that you can come to expect. It's a lot like the components that we develop in our BDE, Bloomberg Development Environment, or Basic Development Environment, or BDE Development Environment, depending on the context. And so in those components, there is a purpose, there is a description, there is a use cases section. These things were already there in the software itself, so the book kind of follows along with that. We have a description, we have use cases, we also have potential pitfalls, and we have annoyances. And again, I selected 2 feature sections to talk about today that are related. So, the noexcept operator, chapter 2, short title, long title, and controlling sentence. Noexcept operator, asking if an expression cannot throw. And I'll just read the controlling sentence because these sentences don't come easily. These are like expensive sentences. Using the noexcept keyword in its operator form affords a standard programmatic means of querying at compile time whether a given expression, typically involving a function call, can be relied upon never to emit a C++ exception. That's kind of what it is, in a word. Now we'll talk about the description. So there's a lot of nitpicking little stuff to talk about in the description, but we got to do something there. So this is just a basic guide before the description. One of the things I wanted to mention, the book doesn't really give a lot of opinion. I am used to giving a lot of opinion when I'm talking about architecture, but what we tried to do in this book, there are no shoulds. There's like, if you do this, this will happen. And the way we say should is we put it in chapter 1, 2, or 3. We put it in the use cases or the pitfalls, but don't actually tell you what to do. But if we say it's a pitfall, we're kind of saying you should not do this. That's the idea. So that's what the noexcept operator does. It lets you ask a question. In an abstract illustration, I say run algorithm, and I have this compile time if that I've thrown in here, and I say noexcept some function. And its compile time predicate says, if this thing will not throw, then go ahead and do this stuff. Otherwise, go do that stuff. And only one of those will ever appear in the code for any given compilation, right? You won't have both sides of the if because the compile time one will be elided. All right, so noexcept, the operator, has conservative behavior. It doesn't try to figure out whether the thing is going to throw. If there's any part of the expression that could throw, irrespective of the logic, it's going to say that it can throw. So I'm just going to give you some examples here, and look at the second and the third one, and now look at the fourth one. You see what's going on here? It doesn't matter what the logic is. If there's a throw in there, then it can throw, period. That's, yes, sir. Yes, oh.
Can you just go back a slide?
Can I go back a slide? Oh, yes. Okay, so first thing is I'm doing 11 and 14 only. One of the things in the book is I didn't want to take anything that was not 11 or 14. And in fact, let me say, thanks, Bryce. There's another thing. We also, when we presented these features, if you can imagine, suppose you want to know about noexcept, but you don't want to know about braced initialization or variadics or what. We tried our best to explain each feature in terms of O3 code. That's not an accident. That's exactly what you want. If you don't know anything, you want to learn the new feature in terms of what you know. Then when we get to the use cases, the last use cases tend to blend a little bit. So you can get almost all the way there, and then you get a little interaction. But that is by design. I hope that answers the question. But thank you for saying that. So anyway, this is one of the things we did when we were going through this. We found a lot of compiler bugs, surprise, because the thing that we do is to learn what it does, we try to write test drivers that explore the edge cases on many compilers, and it shouldn't be that astounding that the basic stuff works most of the time, but the edge cases are all over the place. So we created quite a few things as we went here. By the way, in C++17, we don't need those quotes, but because it's only 14, we left them in so as not to confuse people. Okay, so another thing about this is only the function declaration matters. So you can see here that whether it throws or not in the body, if it says it doesn't throw, it doesn't throw. And then if it does throw, we terminate. Okay. So compound expressions. No matter how you compose them, if anything can throw, it can throw. So I'm just going to go through this fairly quickly so you get the idea. You see that? If both of them can't throw, then they can't throw. F can't throw, but G can throw. So you look at the bottom four, speaks for itself. And then you can change that to other kinds of composition. And yet other kinds of composition. And then you might start asking questions like I would ask, well, what about this dude down here? Or say true or G2. And it turns out that doesn't matter. As far as the definition is, there's something in there that can throw, then it can throw regardless of the logic. So then another interesting thing about what's generated with noexcept, the compiler does some interesting things. And when you have something like this, for example, the compiler, you just have all built-ins. The compiler will generate these things, and they won't. It'll do basically the right thing if what you are trying to do is just sort of do something on the fly. As soon as you try to do it yourself, then we get into the problems. So if you look at all of these things are noexcept because we just didn't do anything. They just are, because the compiler generated them that way. When we try to do it, however, it's not going to work that way. So I'm just going to show you what is obvious. But there's that exception to the exception where the destructor is that way, and you have to go the other direction. There are all kinds of good reasons for how we migrated from C++03 to C++11, and it was deemed that this was the way to do it, and here we are. So that's assuming that this is an empty class. If you had something else, could be different. Now, if you try to default them, now you're back to this situation because the compiler knows what it's doing and it won't cause them to throw, so this can actually work. Now we have inheriting and containing, and I'm just going to show you that this is what happens. I put it up here so that you can know that in the book it will go through all of the things that we're talking about. These are sort of details, not that important to get on first blush, but these are issues that you want to follow, that you want to understand. So applying the noexcept operator to move expressions. Here's our friend std move. We talk about std move in the book, and we talk about R value references and such. But in order to explain this feature, we kind of do have to mention this other stuff. So we refer you to it in the book, but we get you as far as we can. And this is an exception this is an example where in one case you do one thing or the other, but the second one is an example where you say, I'm either going to be able to do it or I'm not going to compile. And those are two ways of using the operator. Okay. So let's see what we've got here. So here's an example where we have both copy and move. And both of them, because we defined them, are noexcept false. If I put this throw in here, and why did I put throw? I wanted you to know that throw in C++ 11 and 14 works. It gets the job done. It's like noexcept. So that gets the job done. And I could have said whatever I wanted here. But they chose to use this word. So that's what it is now. And we have a noexcept operator, and we have a noexcept specifier. I'm not sure that was the best thing to do for people to read, but, well, it is what it is. So here you have an example. You have a function that takes an L value reference, a function that takes an R value reference. And we're going to go to the next slide. and now you see, here I have a test. The compiler will make that move automatically, and that has to do with value categories. We talk about value categories in the book as well. Here's an example where we have a function returning an S, and if you look at this, the compiler will do that. Then we say, how about this one, S1? Now we've got a named variable, and we say, is the compiler going to do that? No. And then we say, wait a minute, is the compiler smart? What about this S2? Well, that S2 isn't going to be used anymore, clearly. So certainly it'll do it, right? No, it won't. Will not. And so these are the kind of things you have to understand what the designers of this thing had in mind, and they made certain decisions, and they erred on the side of safety, and so it doesn't do it. But not knowing all of these things, and when I'm exploring it, I found it was very interesting to go look at the corners. So then we have, all right, where are we here? Okay, so now we have this thing here, and we say, okay, let me do std move, and now I'm going to tell the compiler, I really promise you it's okay, and then everything's fine. There's not an issue at all. So it's all good. All right, so then we have some more of this, applying the noexcept operator to move expressions. And the thing here is, if you don't have a move constructor, all you got is the copy constructor, then that's what you're going to get if you try to move something. Unless the thing you're trying to do throws, in which case you're not going to do it. So to be a little bit clear here, this right here invokes C's copy constructor, and again, this invokes C's copy constructor, and that invokes C's copy constructor because C doesn't have a move constructor. Now, S1 declares a noexcept true move constructor. C1 declares only a noexcept false copy constructor. So if I try to move that, it can't. Now, if I assume S2 is like S, but it has a move constructor is not declared explicitly with throw, then we get that. And assume C2 is like C, except that its copy constructor is declared with a throw. And then we get this. So hopefully this gives you an idea of how things behave between copy and move, and when things throw and when things don't throw. And again, I'm throwing out sort of the kinds of things you need to think about when you're writing code like this. This is not the whole story, but it's an idea, and I'm trying to get through it. Now, interestingly, in C++17, throw becomes actually a synonym for noexcept, and in C++20, it's all gone. So none of the old standard dynamic exception stuff remains. Okay, so we get rid of the throw, and we just put our little noexcept there. Okay. Use cases. How are we doing here? Does that say 71 minutes? Okay. So the noexcept operator use cases, it's really there for things like pushback. If you want to insert something at the end of a vector, you want it to have the strong guarantee. And if it has the strong guarantee, then we have to make sure that we don't get to a halfway state and have to come back. So move operations can make things significantly faster. And I want to emphasize, it's not always faster to move than it is to copy. It depends on how many accesses you have afterwards. And we'll talk, there'll be a footnote at the bottom. So move operations typically don't throw, and I really want to say they really shouldn't ever throw. And anyway, copy operations are typically not declared noexcept. And the rule of 0 allows C++11 to generate these things so that it is backwards compatible with legacy code. Now, the move operation itself, as I said, might be faster or it might be slower depending on the accesses. We wrote a paper just to demonstrate the parameters in sort of like a hypercube way, and you can look and get a feel for when moves and accesses and copies, how they interact. But that's not for this one. What is the strong exception safety guarantee? So if an exception is thrown during an operation, the entire state of the object remains as it was before. That's the idea. We can't always achieve that, Sometimes things escape from the system, but that's the idea. And in the case of std vector in particular, inserting an element at the end of the vector has the strong guarantee, whether it's insert or whether it's pushback. If you're inserting at the last element, that is the way it's defined. So, what? And more. And more, right, there are more of them. Marshall pointed out that in place back is another one, and that's in the book, by the way. So anyway, we're going to create a pedagogically fussy object that we might use for testing purposes. And this one, I'm just going to show you, it's going to keep count statically, and the third time it tries to copy, right here, it's going to throw, okay? So let's just look at what the test driver does. And again, there's nothing fancy here. It's just going to go through the motions of creating the vector and then doing the reserve and then pushing back twice. And this is what they expect the state of the vector to be after we've done that. Does that make sense? Okay. Then we get to the third one, and we insert the throwing element. Here we go with the try. Here's the catch. And then this is what we expect afterwards. And this code should just work. The thing will throw, we'll catch it, we'll go down to the bottom, and the program will execute correctly. It's what we intended. This is how we test things. I mean, there's more elaborate ways, because what we'll do is we'll take a true test, and then we'll start a counter that says throw on the first allocate, throw on the second allocate, throw on the third allocate, until finally we get enough allocates to complete. I think that's something that Dave Abrahams pointed out many, many, many years ago, and something that I was doing when I read that he was doing it. So it's, that old phrase, whatever, minds and such. So here's a simplified myVector class. And really, the reason that this is such a big part of the talk is this is the reason why we have the noexcept operator. And everything else is kind of what? So I thought I'd explain why we have it. And for this reason, it's good. I mean, assuming that you have to have a strong guarantee. So we have this vector, and here's our collection of elements, and here's the capacity, and here's the size, which is really the number of elements, which I wish we called the length still to this day. But anyway, so we have the vector, and we initialize it, we create one empty, and that's important. We wouldn't want to initialize the vector with an allocation in case we have a lot of empty ones, so that's a good decision. We have some safe, effective implementation. We have this reserve thing. Reserve might throw. Okay. And then swap. And swap really can't throw. If swap's going to throw, then we have a serious problem. And of course, that's noexcept. So implementing myVector pushback. So implementing myVector pushback is a pretty easy thing to do for really good library developers. But if you're not a really good library developer, it's not quite as easy as it might seem, and especially now that we're in C++11 and we have some fun stuff, you've got to be aware of some real subtleties. So let's go ahead and do this. I'm going to try to demonstrate what it looked like in the old days. So here we go. So here's my main. This one's going to throw on the fourth copy. I changed my mind. So here's S. S allocates something just because it can. So S is an allocating type. Doesn't have to be. Here's a vector. And now I'm going to push back something onto the vector. So what do? I create a temporary, and I push something back onto the vector, and then what do? I've made that copy, and then I do a swap. And once I do the swap, it all goes away. It looks like that. Then I come along and I do my second pushback, so I create a copy. Then that's a copy. It's the second copy. This is the third copy. Then I do the swap, and I'm back to this. Now I've done 3 copies so far. Now I go to do the fourth copy, and 4 copies, boom, it throws. That goes away, and there we are. And we have what we wanted to achieve, which is the strong guarantee. All good? That's the old way. Now, we're going to implement that. So we say if size is less than capacity, this is what we're going to write. That's great. And we're done. If it's not, then we're going to resize, and now we're going to write some more code. And now we're going to say what we do when we push back. And this is when we have a throwing move, it may throw. So we reserve our capacity, and we keep doing things that might throw until it can't throw anymore, and then we do the swap. So that's what the code looks like. But this is not the most efficient way to do business. We could do better. So we need to ask the question, may it throw? And what does that look like? So right after the resize thing, we have to write this. And the way we write that is we write the good stuff underneath, and then we have to ask the question properly. And asking the question properly is the part that requires a little magic. So here we are in main, fourth copy. And this is what we're going to try to write, by the way. So what's going to happen is we're going to do the same thing as we did last time. This time, we made one copy. Here it is. Now we go to do the second one. And now, that's the copy. We've copied the prototype to the end. And now we're going to move the other one over. So we saved ourselves a copy. Still two copies. Now we're going to do the one that, remember when it blew up last time? And we still have three copies. We do the swap, and lo and behold, still three copies. It worked. So it's more efficient to do it this way. That's the theory. So how do we implement this? What goes here? So I'm just going to show you the implementation. Notice we're using new there. Notice the first thing we do is we add the one to the end, and then we go through and move all the rest. But when we start moving all the rest, it can't throw because we have a no throw move constructor. Is it a, yeah, is it a constructor? Could be no, it's a no throw move constructor. That's right. Just want to make sure. And then notice this thing that this move and the stood move and the derivative, that's a lot of stuff going on there. And then we're done. We're committed and we return. So this is taken care of. But take a look at that. That's the thing that we want to make sure is no throw. And so that's what goes there. Now, if you look at that, maybe that's not what you would have put there. But that's what has to go there. If you do something different, you might find one of the bugs in one of the pitfalls or one of the annoyances in how all this stuff works. So,
John,
yes?
can I just write stood as no throw move constructible there?
Oh, you absolutely can. We'll get there. Absolutely. Absolutely. Remember, there are things you can do in the library, but you have to know not to do the dumb thing. You know what I'm saying? So, and again, I learned almost all of this from Alistair Meredith. I have to tell you. So if you doubt my veracity, send him an email. Send me an email. I'll send it to him, and I will get it clarified. But I remember working on this with him for quite some time. Yes, in the back.
I want to confirm, is that null pointer in the noexcept operator, that's okay, right? Yeah.
Yeah. Yeah. If this were wrong, I'd be in real trouble. Yes.
Yeah, and the reason is that the noexcept operator doesn't actually evaluate anything. It's just looking at the types, basically. So you just need a void pointer there. And in fact, the thing inside stood move, you just need a T, right? It could be any T, but that's a handy T.
Yeah.
Actually, you need a T ref, but whatever.
And we went out of our way to create the address as a void star because we didn't want it to be a type thing. I mean, there's a lot of shenanigans going on to make this all work. But that's a good model. If you do that, yes?
With the null pointer, isn't that though testing the placement new as opposed to, is it, okay, there.
Yeah, but that's yes, it's testing the placement new, which is exactly what we want to do. Yeah, and the reason we want to do this is you're going to find out that if you do something else, it has some baggage that comes with it and gives you the wrong answer. And yet, yeah?
Is there any difference between these expression and using the move constructible no throw, is no throw move constructible trait?
Is there any difference between using the operator and using the trait? The trait is what does this magic for you so you don't have to know all this good stuff, right? I think that's the answer. I got two more people. Go ahead.
I believe there was a defect where the traits accidentally also tested for the destructor being used.
So what was said is that the trait didn't do a good job and that had to be corrected. I believe you're right. Yes?
And you're sure that drap is a real pointer and not something fancy that overloads the bracket operator?
Because we did the void star. Yes, Marshall.
The
No, no.
drap?
What he's asking about D or AP, is that a raw pointer or a fancy pointer? It's a raw pointer because
Okay.
it's declared, it's a member variable in the
Because
class.
otherwise you would have to put the brackets also in the noexcept.
No. That's just a raw
Okay.
pointer.
It's just a raw pointer. All right. So we could enforce the no acceptness of something using static assert. And I made up this cute little example where I have something called sign, and it's a function. Here it is. It's not, no big deal. It's just a function that calculates the sign, and we include math, and look what I did. So that is the function. Now, why do we want this thing not to throw? We might be in a situation where we need to calculate the sign and we don't want it to throw. So we can add that. This function does not throw. Guess what? Now the function doesn't throw, right? Because we said so. Now, to make sure that it doesn't, we add this. Now the function doesn't throw, for real, right? We said so, and it can't. So now, this is where we go from the over the edge. Now we add no except. OMG. Why did we do that? What reason? Why did we add this? What programmatic thing is going to check this function to find out whether it throws and then do something different when it can't throw? So whoever would use that no except is not thinking clearly. So I would tell you that no except is faulty thinking. And you could say, well, there are other reasons for doing it, and we will get to what those reasons are and either agree or disagree at that point. Did you have a question?
Well, a comment. You are asking or saying that this is a defect in the code, that the programmer doesn't have clear thinking. But if you're going to use no except at compilation time for expressions, and to guarantee that you are going to be able to provide the strong section safety guarantee, you need to first make sure that the things that you call are no except, and you don't know what you're calling.
Okay, so I think what was said is we need this because somewhere in the code it's going to check that.
Yes.
And I claim no, it is not, because nobody's going to call this function in a conditional, in a compile time conditional, to check it because they already know the answer before they start. Yes?
Why does that apply to the sign function and not to perhaps the multiply or addition operators for the user-defined types that could possibly be passed in? Those should surely be declared no except to satisfy the static assertion, right?
Okay, so the question was, do the individual operations have to? Remember that if any of those operations, if anything can throw, then that thing can throw. And the question is, does that expression throw? That's what we want to know. Does it throw? If the answer is yes, then don't compile this because we don't want that to happen, right?
What enables that static assertion to be useful is that potentially user-defined operator overloads for multiply and add were declared no except, right?
We're going to get to that point.
Okay.
We're going to get to that point, yes. I see what you're saying is, in order for that to work, the operations themselves have to be no except.
Yes.
I'm saying what I'm ultimately, yes, go ahead.
No, you finish your.
What I'm ultimately saying is all of this stuff to make sure that something doesn't throw is overkill because it means that if it isn't, which we're about to see, I'm about to make that point, if you don't do that, if you don't have the complete no except chain all the way through, then it'll get rejected, but it might itself say, it might say that it doesn't throw. Like the whole thing may be like as we do in the standard. Before we had no except, we said does not throw. For the bracket operator, we said does not throw. We don't put no except on the bracket operator because when you call it out of contract, you're making a statement about something that isn't talked about in the precondition, so you're over-specifying the function. There are reasons we don't want to do that.
I think when you put no except, it does not throw because it'll terminate. And it's not like a...
Oh, in that case, it does not throw, it won't compile. But the point that I'm trying to say is, if you put in the contract for the bracket operator, you say does not throw, then if you call it satisfying the preconditions, then it doesn't throw because that's what the contract says it does. And if it does throw, it's a defective function.
Sure, but we're talking about the no except specifier.
Right. Putting the no except specifier on this doesn't add anything but the ability for the no except operator to query whether this function throws.
Well, it goes more than that. It guarantees that doesn't throw.
Okay, the term,
Terminate
but you say guarantee, but when you have a function called sine, what guarantees that it doesn't return the cosine? It says it returns the sine. Now, if you're a reasonable person and you write something that says, I return the sine, then it's your job to make sure it returns the sine.
The no except is the compiler guarantee.
I understand there are many ways to add. You could have static analysis. We could use unit testing, do lots of things. The point is, once you put it in the contract, in the signature, now it's no longer something that's currently true or whatever. You've specified for all time and whatever this thing. When maybe that's not what you meant to do. Maybe what you really meant to do is say, oh, I have some optimization I want to achieve that's not a query of the no except of the operator. Do you see what I'm saying?
But that's a different question.
That's a different question. So in other words, there are cases where it's true that it doesn't throw, and adding no except doesn't give you don't get any more programmatic ability to do anything with it. What you do is you get something that you're stuck with, you can't go back. It's one of those things you can always make something no except that wasn't. You can't take it away.
It may be true for template functions, it's not true for regular functions in terms of separate compilation.
I'm not talking about that. What was just said is it's not about compilation. Once I make a promise to you that I won't throw,
Yes,
then I can't take it back.
I agree.
Okay.
But when you were saying that adding the no except here doesn't actually give you anything more.
Except for the ability for a no except operator to query it. And I'm saying, who would do that? Think about it. Let's think about that some more. Like, who would write code like that? Okay. You would write code like that. So,
Oh, well, John, the other thing is that there's not going to emit a landing pad. If the definition of a no except function doesn't have any internally potentially throwing expressions, it's not going to emit the exception handling CRUD and then force the backend to elide that garbage.
right, we're going to get to that. That is definitely a different issue. Now you're talking about the kinds of optimization, and we're going to get there. Maybe. Not sure. Okay. All right, so standard containers have to follow they have to deal with all kinds of stuff, but we don't have to. And what I was trying to say is non-standard containers might just simply choose not to handle code that has throwing moves. It might just say, I don't choose to deal with you. And then if it does that, we could write a cheaper standard container or non-standard container that just gets you to the point, uses the static assert and says, if you don't behave the way I want you to, I'm not going to compile for you. It just means that there are preconditions or requirements on my type that are stronger than the standard containers, which are more forgiving. So this is what that would look like. We're leaving out the whole part where we're saying we're going to handle it if it's a throwing move. We just say it's not a throwing move. It's a non-throwing move, done. So I just put that up there, lot to look at, but the green is really what's going on. And it's just a subset of the other implementation. So other use cases. So move if no except, vector pushback of this was in place, these kinds of things. These are things that we can do. Pitfalls. Using the no except operator directly. This is some fun stuff. You see how I'm using no except and no except. This is a conditional no except expression. Chapter 3 feature assumes that there is an accessible default constructor invoking the destructor as part of the constructor subexpression. So this is where you might have thought to do this. And if you do that, you get something you didn't expect. So we have something called declval, which I have never, ever used, but believe it actually does something useful. And this is what it does. We can use declval. Whoops, hold on, sorry. So if we use that here, we invoke this invokes the destructor and does not invoke the destructor. So even if you use declval, you still have to use it just so. Okay. So again, this is beyond my skill set for being able to write code. I would have to cheat and look at the slides. But I'm saying that these are the kinds of things you have to know to do this stuff properly. So it's not all that easy. Doesn't parse the body of the function, so doesn't matter. Look at this. The compiler may be able to help you and may not be able to help you. Object code optimization is coming up. We're going to talk about that. Annoyances. So the noexcept operator is too sensitive for direct use because it picks up sub-expressions that you didn't intend. And so there are traits, and we can do things like this. And this is a good thing, except the traits didn't work at first, and now they work better. And the traits and many other things have evolved from 11 to 14 to 17 to 20. And it's interesting exactly what constitutes, the definition of what is trivially copyable and what it means to be that. And it's kind of interesting. They got a little bit more fancy, and it's explained in the book way beyond the scope of this talk. Anyway, so here are some things that we have, just putting it all out there. All right. So the strong exception safety guarantee itself, if it had been up to me, I wouldn't have tried to support it. Dave Abrahams claims that I'm completely wrong. I accept that. But I think it's an overreach. I think that the amount of machinery that we have to go through to make pushback a no-throw, a strong guarantee is unbelievable, the ramifications that caused. But the recovery path, when something fails, you don't typically recover an object. You recover an entire frame, an entire transaction. So to me, this doesn't really make a whole lot of sense. So I put all this stuff up here just saying we can use copy swap typically on the larger situation if we need to. But making it built in every time, that was painful. There's certain change in behavior. I don't know if everybody knows this, because I sure didn't, but Alistair does. And here's an example where we're doing something in main, and we wind up having to grow the internal representation, and all of a sudden, the capacity of one of the inner vectors goes from what we set it to 0. Whereas in the C++11 model, because we're doing a move, the state is preserved. And so we actually get that. And I'm like, cool. This is very cool. It's a change. So C++11 is not the same as C++03. Maybe it's better. Not true. It doesn't have that problem for a string. A vector string doesn't have that problem. But that's just something neat to understand. So if you can explain why this is true, maybe there's an interview question. Why is it that in 03 it's like this and in 11 it's like that? If you fully understand this talk, then you can answer that question. So that's a homework question. Just make sure you understand why that's the case. Okay. Destructors default to noexcept. This is kind of weird. User-provided move operation will not. Seems a little inconsistent. Probably was necessary. We just don't think that throwing moves are to be respected at all. We just don't care to think about it. Older compilers invade the body of const expr functions, so that was a little annoying, and that stopped. So this is what we had. Anyway. Anyway, take a look at that, and you can just see that some things can be buggy. All right. We're done with that. We still have some time. Does this say that I have 45 minutes left? Is that really the truth?
Yeah.
We might actually get through this.
Or you could look at it, you spent 45 minutes already.
Yes. Awesome. Noted. All right, so let's look at this one. This one is a Chapter 3 feature. People would say, why is it such a big deal? Well, it seems to be a paradox, and the fellow who gave the kidney for this, it was Dave Abraham, said that it was a horrible idea and he wished he didn't have to do it. And I remember when he was doing it, and it seemed like there was no other alternative at the time because we were at the 11th hour and we needed something because the whole thing was busted. So he had a very, very nice presentation of something that went up in flames when the move constructor threw, and it was awesome. Very compelling. But anyway, I think Strustrup said something like that in his book, The Evolution of C++. He was convinced by many people with persuasive arguments that protected was a good thing. And he later said, beware of people with persuasive arguments. So that stuck with me. So the short title is noexcept specifier. The long title is the noexcept function specifier. We couldn't think of anything more clever really than that. And this is worth saying. A function having a noexcept exception specification denotes a programmatically observable, runtime enforced guarantee that no thrown C++ exception will ever escape the function's body. If that's what you want to do, this is yours. It's good. Absolutely. That's what it does. Whether you want to do it, that's another story. Now, what's the description? So the primary purpose, denote explicitly when a function is, particularly a move or swap operation, may throw. Particularly those. Possibly conditional noexcept specifier provides precisely information at compile time. For non-generic code, the unconditional form usually suffices, and for generic code, or to override an implicit noexcept, the conditional form is required. Okay, so here we are. So right now, this is noexcept false. We put noexcept on, and now it becomes noexcept true. Pretty straightforward. Conditional noexcept specification. So noexcept, compile time, constant. So overriding implicit, noexcept true. So if you have like that, okay, so struct, here we go, noexcept false. The destructor may throw. Generic function. Okay, this is a really interesting use, right? I'm saying that the thing won't throw if the size fits in the pre-allocated buffer. That seems like a very reasonable thing to say. Like, I get that. I like that. Okay? But you have to mean it. Generic context in a class. So now I have something that wraps something, whatever. And the thing is, I don't want this thing to lie. I will want it to lie later. But right now I don't want it to lie, so I want it to say, yeah, I'm noexcept if the thing that I've got is noexcept. So that makes sense. Kind of like that. If this is what you want to do, you know. So now, okay. If that's important, if somebody's actually going to make a decision based on that information, by all means, let them know. Okay. So notice I've got the red and the orange yellow. The noexcept specifier is the one in red, and the noexcept operator is the one in yellow. And they look just like each other, so I colored them differently so I could remember which is which. All right. Now, look at this. What we're doing here is we're saying this thing is noexcept if the body of the function is noexcept. I don't see how this could be any more de-encapsulating, right? You basically put the body of the function on the line. This is annoying. What?
Go look at stood less void. It's even worse.
Okay, I was told by Marshall to go look at stood less void.
Void. Void. The diamond. Stood less diamond. Yeah.
Oh, I see. Okay.
Because you get 3 of those.
All right. Well, that there is something worse than this doesn't make my day in any way, shape, or form. This is bad enough. And suppose maybe we need something better than that in the language anyway. So look at this guy, noexcept F. Somebody might write that. Somebody might write that. If they write that, they get this. If they write that, they get this. Ouch. Now, to seasoned people like Marshall, this is obvious. To me, they look the same. You know, it's like, ouch. All right, so that's just, oh, sure. Back we go.
Why is there context pre-developed in the first one?
Because you can't put a thing that has to be evaluated at compile time.
Oh, that's a specifier, not the expression.
Yeah.
That's why you color code.
And that's in fact his complaint, is that people confuse the specifier and the,
Well, it's especially
And,
confusing when there's no other context.
Yeah.
I'm just saying it hurts my head.
Yeah.
If it hurts your head, then we know we have a problem because I know what's in that head.
It's all these people that are afraid of adding new keywords.
Yeah, I am furious still with the perfect forwarding and using the double and for that. I'll never survive that. Never. Anyway, I still think that should be made 3 or something, anything.
12
I think so, 12. At least 12, or maybe 12 to 14. Have a range for expressiveness, you know, creativity. You want to stifle creativity. Okay, so anyway, this is the violating exception specifications and the old dynamic kind and this one now. The difference is that the noexcept is a leaner, meaner kind of thing. The other one was more articulate. I'm not convinced that if people really wanted to, if they really did, they couldn't have followed that. This is just less combinatorically annoying because it's either it throws or it doesn't. And that seems to be all that anybody cares about anyway. So overriding, so here's something, this is the way it used to be, yes. We used to do this, you couldn't override it. And then it was determined that that's a bad idea because we can't really implement that well. What if we did something different? What if this is the way it was in 11 and 14, and we said, we can't really implement it that well, and it's not that useful. Maybe we want to do something different. What if we just let it work? So as of C++20, the rationalization is, well, what if something can throw, but you want to say that it can't throw so you can fool the compiler into taking a risk and letting it throw? And if you know that it's not going to throw because you know it's not going to throw because you know, or you're not going to use it in a context where it's going to throw, or you don't care if it throws because it's so slow the other way that you just as soon have the thing crash if it runs out of memory, so be it. And I thought that was a great answer. So from an engineering perspective, this is how it works now. You just go ahead and if it happens not to be true, so be it. It just works. It just works the way you want it to be. You just tell the compiler, this is what I want, instead of the compiler telling you, no, you can't. You say, yes, I can. I like that. Compiler's not in charge. So function pointers and references in 11.14 kind of pretty much work. They're not part of the type system yet, so they still kind of do sort of the right thing. And so I've got some examples here just to show you. Didn't want to necessarily teach the whole thing, but you can pretty much imagine that it's what you'd expect. You can't have the pointer to a function or whatever that is that gives you more capabilities than the thing you're assigning. So it's that kind of thing. So this is constraints on virtual functions, and it's just an example from the book. I put it up here. It's like too much to read. The idea is when you're dealing with something from a base class, you don't want to have something in the derived class that is more throwing. There's more likely to throw than something in the base class. That's really just basically the overall idea. So in short, a virtual function can throw only a subset of what can be thrown in each base class. That's really the be all and end all. So that's that. Can be an annoyance because sometimes you know better and you say, I know in this context it's going to be fine. Anyway, so explicitly declaring declaring a destructor noexcept false. You can do it. That's why you need this. You need to be able to say that this thing actually can throw, and just really bad idea. But I already said that. All right. Now on to use cases. So the use cases really come down to algorithmic improvement. If you can do something algorithmically better, absolutely. More operations involving the strong move operations involving the strong guarantee. You have to do it for the standard. By all means, let's do that. Now, we can reduce object code size, maybe. And we do that by suppressing exception handling code across translation units. Across translation units. Interestingly, when the compiler is not allowed to invade the body of the function, it's not allowed to do it for semantic reasons, but it is allowed to do it for optimization reasons, which is infuriating because it conflates two things. So for algorithmic reasons, great, but you want to state this and you say, yes, this is in my contract and I never will change it, this is good, and all the code in the world is going to be good because of this, and life is good. Then this one is a little more dubious, and this one's a lot more dubious. And so we're going to talk about those guys. So, okay. This is low cost, high reward. These are high cost and low reward. Surprisingly low reward, because if what you're trying to do is make your code run faster, you are wasting your time. We will explain. Declaring non-throwing move operations, non-generic types. So if there's something to benefit, great. Here's an example. I say that the move constructor is noexcept. That makes it faster. Things can ask, are you going to throw? Your move doesn't throw? Then I can do something faster. That's great. I don't have to do the much more laborious copying. Great. Generic types. So we can do something like this. We can say, if the thing that is coming in isn't, then I'm not. So this is a really good use of the noexcept specifier. I'm totally on board. Here's another one. So does this make sense? This is what it was written for. This is what it was designed for. Then people started fiddling. And they said, well, I could use it for something else. You can declare a non-throwing swap. And it turns out that you can make a swap noexcept in cases where even you might not be able to make a move noexcept. And that's specifically when there isn't a no resource allocated state. In other words, the radioactive state or the subconstructed state. So there are cases where you can do good things because everything has the resource. There's nothing that has the no resource. If it needs the resource, it's constructed with it. But there are problems with that. And we expect swap to be noexcept. So here's the example that I think is really cool, where we have, suppose we know either that any move operation that can throw won't, we just know that, or we don't care because the only thing we could do if it did is terminate. In those cases, we could create a wrapper, a generic wrapper called noexcept move wrapper, and it takes whatever you've got and it just implements the noexcept versions of that. And so it just strips away all of that noise and lets it be used in a container. And it turns out that prior to C++20, you'd have to implement those defaults by hand because it wouldn't let you default it. But now it'll let you default it. Awesome. This is actually engineering at work. It's not as safe, but it's what you want to do. So once you know it's what you want to do and the compiler stops you, that's when you get angry at the compiler. Yes?
If you implement those by hand, there's no way that noexcept move wrapper could be trivially copyable. And this way, it can be.
Okay, so it was just pointed out by Marshall that there's an added benefit to the default thing. So it has the benefit of being trivially copyable. It could be trivially copyable. All right.
Marshall, but if the base would throw, it can't be trivially copyable.
Okay.
Because the sub-object
Yeah,
move
but in the case where the base object was trivially copyable using default, noexcept move operator is trivially copyable, but if you implement it by hand, it's not.
Right, but you'd have to implement the throwing part of the base by hand. So that the base sub-object would be non-trivially copyable.
Yes. I think we're in violent agreement here.
Right, okay.
All right. Since we all agree, what was the conclusion?
That my conclusion is that that by using equal default, you open up the possibility that noexcept move wrapper is trivially copyable and trivially signable.
So,
where before it was not ever.
so what was said briefly, it's just that now that we can use default, we have an additional possibility of getting a trivially copyable thing where before that was not going to be the case.
Not ever.
Ever. Okay, good.
I don't know what T was. T could be an int.
T could be an
It
int.
would not be trivially copyable.
We have now a new theorem. Excellent. All right, reducing object code size. This is important. Less code runs faster, right? Pretty much all the time. You know, Duff's device is one of those examples where it's more code, and before compilers got really cool, Duff's device was something, made a difference, right? Typically that's true, but it's not typically true with exception code. Particularly because the way we do things, all modern compilers now use the zero overhead, what is it, the zero cost method. And that is completely different from what used to be where there was code that could cause cache pressure. There is no cache pressure. There's nothing. Zero. That's why they call it zero. Okay. By the way, if you are liking exceptions and feel that everything needs to be noexcept, you are a little bit of a split personality here, because what if you get everything to be noexcept and then turn off exceptions on the compiler? Like, that's the ultimate noexcept. So we really need to think about what we're trying to do. When we're making things noexcept, we're making them exception unfriendly, right? The more things that are noexcept, you got to be pretty sure that nothing throws. And if you accidentally have something in the bowels of whatever that comes up through a noexcept, you're done. So just know that. Just know that there's a little there at odds. Tension, that's the word I'm looking for. Thank you. There's a little tension, like it. Okay, when an exception is thrown, the destructor of all non-trivially destructible live objects in the current stack frame must be invoked. That's what we're saying has to happen. If you say that those things don't throw, then they don't need to happen, because there's nothing, that whole thing isn't the case, right? When an exception is thrown,
The structures have to be run.
the structures have to be run.
Whether they're noexcept or not.
Whether they're that's true. I retract what I just said. Putting the noexcept there allows you not to have to guard against what if they throw. I misspoke. Thank you for clarifying that. So, user provided, hence non-trivial destructor. Here's that, and here we've got the function GG. I use F and G consistently throughout these things to talk about the inner and outer function. So F is the outer function and G is the inner function. And the first call to GG, no object code overhead, because it either succeeds or fails, right? There's nothing, there's no problem. Then I create this. This is some state on the stack. Now if I call 1 and it throws, there's some object code overhead, because I have to try, catch, and do all that good stuff, right? Then if I do this, there's yet more object code, right? So what we're trying to do is we're saying if we declare GG noexcept, then there's no object code here, no object code here, and no object code here. Does that make sense? That's what it gets us. Yes, that's the truth. Okay. Now, I make FF also noexcept. No object code overhead, no object code overhead, and what do you think here? None. But if I do this, now we get some object code overhead, more object code overhead, yet more object code overhead. So what's interesting is there are 4 combinations. Yeah. So there are 4 combinations. And I'm saying sometimes it's better, sometimes it's worse, right? You just have to know what you're doing. Now, who cares? Why do we care about the object code? The object code is not slowing us down. The object code resides in a segment of memory, ideally, that never gets loaded into the processor. Never comes in, it's just sitting out. It could be out on disk for all I care. Because that code doesn't get paged in until an exception is thrown. So how could that code that's sitting out on disk slow down your program? That just...
It's the same, it's going to be the same 4K iCache page, right?
No, I don't think so. The reason is that the way this stuff is implemented, it's separate, physically separate from the running code. There's nothing being brought in. You have to have you'll get a page fault when that happens. And then you'll have to go out to storage and bring in the thing, and it's slower than slow. It's the slowest thing that ever happened in the world. It's designed that way because exceptions are exceptional. Everybody keeps saying that. So when you throw an exception, you better be prepared to wait a long time before that exception is taken care of. That's the deal. You're not buying it. Okay, I understand that this is a hard thing to do. We actually measured it. I know it's crazy. We actually measured this stuff. If you contrive it to be what we want it to be, if you contrive it, then you can squeeze out an instruction, but it has to satisfy a very particular property, and I'll show you that. But if you just try to do it at random, no. It's not. I'll explain. Anyway, making FF noexcept when it cannot know that nothing in its body may throw typically increases the size of FF by one call to terminate. That's just what happens in this case. But let's continue, and you can doubt me. I'm still going to put up some numbers. But notice if it's visible, if the compiler can see the code, if it's in a template or if it's in an inline function or if it's defined in the same translation unit in any way, then all kinds of good things can happen. You can look in the body. All right, so reducing object code size criteria. What has to happen? The function body FF contains one or more automatic variables of non-trivial destructor type S. Otherwise, there's no destructor to invoke when unwinding. There is at least one expression in the body of GG that might throw invoking noexcept false function. Otherwise, there's no need to unwind the logic. So these are the criteria. The third one, the potentially throwing expression invoked during the lifetime of one of the aforementioned variables S1 and S2. Otherwise, there's again no need to unwind the logic. So this all has to hold. If you put noexcept on something and that doesn't hold, don't even talk to me. Seriously. Okay, now, reducing object code size, tiny benchmark. This is one of those things where you take a family of functions and you just try them, and they have like 1 variable, 2, 3, 4, 5, just keep going. And you look at what the pattern is and you try to see, is the noise bigger than the advantage or the advantage bigger than the noise or what? Now just look at it. Well, we'll see what happens here. This is, okay. So in this case, if you look at the 4 ways of doing this, you can see 3 of them are the same, and the 4th one is bigger, and that's optimized and not optimized. So GS is the noexcept. It's a macro that we can either have or not have noexcept. So GS equals noexcept means that's, I mean, this is a 2x2 grid, right? Now we're going to look at this. Okay. Notice the difference. So if the G is before and then the S, it's that. If the G is after, then it's that. Clearly, the size is obviously affected. There's no question about it. If you hit the right thing, right, if you get the right circumstances, there's a difference in size. Okay. Those are exception, to answer your question, those are exception specifications. Okay. Now, potential pitfalls. Overly strong contract guarantee. What is a contract? It's a contract between human beings. It's a transactional agreement. If you give me X, I will do Y. That's what a contract is. Did you have a question or no? Okay. I hear you. Hear you.
My hand way up here when I got a question.
Got you. A narrow contract has preconditions, a wide one doesn't. Okay? If you give me X, I will do Y. But if you give me something other than X, I will do whatever I want, and you might hate it. That's why noexcept on a narrow contract makes me crazy. Anyway, so double square root value. Here we go. Return the positive square root of the specified value. The behavior is undefined unless value is non-negative. That's a contract. The first one is what it will do, and the second one is the preconditions. It's phrased that way because that is how we aggregate preconditions. Okay, overly strong contract. So benefits of not specifying behavior are negative input. The cost of designing, developing, documenting, testing, whatever. We don't want to tell you what square root does when it's negative. We just don't care. So that's that. We leave open the option for mapping different things in different build modes like test, debug, whatever. We might want to extend it and keep it backward compatible. If I said that on -1, it prints a picture of, your cousin, why? So noexcept has that property of giving specification to something when the preconditions aren't satisfied. That's overly constraining for me. So here's an example. I have a business sort. This business sort has added the requirement that it be done in order n times log n time. We added that. Why? Because we looked at the implementation and noticed that it happens to be n log n. What if later we find out that for all the things that that's doing, we have a worst case quadratic, but its average case is so fast for the particular things that we're doing that that's the thing we want to use? Well, that contract screwed us because it says something that we don't need. So if you put that in, you have to mean it. Don't just put it in because I looked and it seems to be true. Same thing for one architecture. You might be able to do something on Windows that you can't do on Linux or vice versa. And if you say that, oh, this does this, oh, and this other thing, then when you get over here, you can't, and it's no longer a portable function. So promise what you need to promise. Don't just promise it because it happens to be available today. And again, the reason for doing this sort of thing is we want to specify what's needed. Don't promise too much. And I'm saying adding noexcept is another way to constrain a problem like that. From now on, whenever you give me something, irrespective of whatever else is in the explicit contract, I will not throw. Who cares? There has to be a reason for that. If there's no reason to put that in other than it happens to be true, no. So now, I really do want to get to the point about well, there's one more thing, no fail. So noexcept, sometimes people confuse noexcept with no fail. Noexcept doesn't affect the failure or non-failure of your function. Noexcept says that there's no point in your trying to catch any exceptions here because if something is screwed up in that function, you'll never see it. So don't worry about it. I got you. That's what it says. So I would say square root, for example, is a no-fail function because you call it. It's not going to fail. There's no resource that it needs to acquire or do anything with. So it's just going to return, just going to work. And vector pushback isn't no fail. And by the way, vector at isn't no fail either. It's just one of them tells you don't do this and the other one says if you do this I will throw. It's part of the contract. But it's not no fail. Unless you consider throwing to be just as good as doing whatever I asked you to do. And if that's the case, yeah?
What do you mean by fail here?
Okay, if I ask you for the square root of a number, and you tell me I don't feel like giving it to you, that's not okay. You will not fail to give me the number. You will give me the number. You're on no fail. If for some reason I ask you the question and I don't get an answer, you failed. Okay. If anybody believes that it's okay, for example, to have a status that says, I'll either return 0, which means I did what you asked me to do, or I'll return a negative indicating that I didn't, and that's just fine, and then you go in and for all those functions, you just hard code the implementation to return -1, that you've done your job. No, you haven't. It's just like telling a painter, I want you to paint my house. Okay, what's the contract? The contract is, give me $5,000 and I'll either paint your house or tell you I didn't. No, that's not okay. These are crazy things. So we don't even think about such things. Anyway, other pitfalls. So accidental terminate. I mean, if you've got noexcept all over creation, you better be careful because if you try to throw through something that says noexcept, you done. So these are these are things, these are the kind of things that just, and the other one, imprecise expression, if you don't copy that expression just right, you might say, well, this is the conditions under which I don't throw, but this isn't the same condition as I had down here, and so there might be that issue. But the most egregious one, the one that just kills me, I want it to run faster. And that's just not true, because there's no code on the hot path. It's all in the cold path. Modern platforms have a zero-cost exception model, and it's literally zero cost. And despite that you don't believe that it's zero cost, that does not affect whether it is in fact zero cost or not. And let me show you some numbers. So even when theoretically possible, so adding noexcept where there's no theoretical basis is just, that doesn't make any sense. But if there is a theoretical basis, like you could imagine, you could conjecture that yes, this could be faster, because there are places where it could be faster, it's still really not typically exploited by compilers. So,
Today.
yeah, well, okay, today. So now what we need to do is we need to say, well, what could we get if we really tried hard? So we did. We have to have a situation where some piece of code can be elided that otherwise, some code in the instruction stream can be elided where otherwise it was there, otherwise it would be needed. So that's what we have to find out. We have to figure out, we have to mechanically construct, artificially construct such a situation. They exist, but we have to find one. So if you want to see something about this actually tried, there's this lightning talk. You can go and look at it. So I'm putting it up here. But this is one that somebody else did. We created benchmarks using unique pointer. So here are the benchmarks. The specific idea is you can declare something noexcept, and we can reduce it by one load instruction, one. That's what we were able to do, but with real code. Now, look at these numbers. These are what this is, object size and runtime. If you look at the object size is very compelling. As you look at the number of instances of the variables, this is the thing where we have, something that has one instance, two instances, three instances. So the function is changing size, and where it hits in the boundaries and what happens inside the computer has a lot of noise. And you can see that these are not always, they're pretty clearly improving, right? They're pretty clearly improving, like compared to one, they're getting smaller and smaller and smaller. That's a good sign. When you look at runtime over here, though, let's take this section. Here you can see when you go from 2 to 3, it gets better because there's more instances of what we're trying to do, so you get more optimization, right? These are comparisons. So one is no change. 0.6 is it's that much smaller. Look over here, though, and the corresponding thing. It got smaller, then it got bigger. It got, you see what I'm saying? It got bigger, and then it got more bigger. So we really need to just look at this and see, is this the kind of thing that you want to crud up your code with? This is something that has the ability to get smaller. That's my point. It has the ability to get faster, whereas most things don't, but this one does. And even with this, it's so small. So I just want, if somebody says, you know what, our code's going to run much faster, we just make everything noexcept, it's going to run much faster. That is false. That is just false. Somebody come up with a benchmark that shows me that, because it doesn't exist, I claim. Anyway.
Hey, John.
Yep.
When you're looking at the Microsoft optimizations there, OS is for size.
Yeah.
Size says damn the speed.
Right. So look at the one that's for speed.
So therefore, but then you're asking it, well, why did my runtime go down when you're saying I don't care what the runtime was?
No, that's perfectly fine. I'm saying, interestingly, over here, when I gave it yet another opportunity to optimize for speed, it got worse in speed. Now, look here. Here it was faster. Here it got slower. Interesting. I mean, forget this. You can ignore that. It's just there for completeness. But look at this. You see where it's slower, faster, faster, slower, faster, slower, slower, faster, faster, slower. It's noise. That's what I'm trying to say. They're not. I have not seen a benchmark that shows that a program speeds up by liberally stringing no except all over creation. Yes?
Are there code gen benchmarks that you've put together? Because that's primarily why I use it.
Code,
For compile time.
I'm sorry, I don't understand. What?
I mean, I haven't measured it, but my assumption is that no except would improve compile.
Okay, so if we're talking about compile time, I don't know. Runtime? No. Compile time? That's another question. And I'm perfectly happy to have the facts say, if you use no except, your compiler runs faster, except you've cruddied up your code with no excepts. What are you doing? What is the overarching thing that you're trying to achieve here? Faster compile times? Buy a faster computer. I don't know. But or more of them. Do them in parallel. I would not crud up my code with no excepts trying to make the thing run faster. No. Compile faster? No. I wouldn't do it. But other people might have a different need. Maybe they can't afford another computer, and they're willing to crud up their code with no excepts, and they're willing to take on the other things, the negatives of it. But I'm saying if you use it for what it's intended, it's awesome. And if you use it for anything else, but that's my feeling. Yes, David.
I think one of the things that's important to consider with this is that when you, as you say, like crud up your code with a bunch of these extra annotations, there's a complexity overhead. So the developer who's developing this code needs to think about it, and then the reader that's reading this code needs to think about it. And I know that in talking with Bjarne, he's very concerned about an ever-increasing complexity overhead in the language, which can make it not accessible to newer users.
Okay, so just to recap, the more that we have to worry about whether to make something no except or not, the more complexity we introduce into the language, and the more keywords we have, the less accessible it is to newcomers to the language. Did I get that about right? Okay, thank you. That was David Sankel. All right, so I'm arguing, it doesn't say this in the book, but I'm saying I think that this is misguided. And I think that people should use no except when it algorithmically improves what they're doing. But even if they really feel strongly about this, we could still have our cake and eat it too. The optimization is conflated. We could have something else besides no except that's exactly like no except and will make Bjorn's head spin. What it does is it simply tells the other translation unit, I don't throw today. Today, which is the same thing it would do if it were in the same translation unit. So it's a hint, and I just made it look like that, does not throw. They do the same thing with respect to optimization, but you can't query it, so it isn't an algorithmic nuisance. So if you can show that the optimization is worth doing, you can put the trait on, and it can do everything that no except does, except it can't be queried by the no except operator. If we had that, we'd be done. Now, would it make the complexity of this thing go up? Yes, it would, but it would allow engineers more flexibility to get the optimizations they want without having to promise something along with it that they didn't mean to do. I believe very strongly that this would be a good addition so that we don't wind up littering all our code with no except in the false belief that it'll speed it up. Anyway, I say that's a good idea. All right, other annoyances, code duplication. It's not part of the functions type until 17. There are some ABI changes, there are sort of edge cases where things do get a little weird in 17. It's not on the function itself, but on the argument signatures. And doesn't trigger SFIN-A, so it doesn't participate in overload, and it doesn't participate in overload resolution.
It doesn't change the signature. No except clause is mingled.
No. No. What you can do is you can, if you have things that, arguments that are themselves have no except things in them, if you follow what I'm saying. In other words, if you have an object, if you have a function, the signature of the function, right, there can be something that is and isn't no except. And that mangling changed because you can't have both, but it is what it's encoded in the mangling that it is or isn't. You can't overload on it, but still it's encoded in the mangling. And I got it. All right. Anyway, That's at the very bowels of the, whatever. It's why this is a lot of stuff going on here. So, yeah. Yeah, so this is an annoying thing because, as I said, sometimes you might not want that in the same way you might want to just decide it's not going to be a problem here. And but I think it's much better to be able to do that than, for example, having to, because I can't do this inheritance stuff, I'm just going to call it a void store because that's even worse. So if the base house has a narrow content. Anyway, I'm just about out of time. I'm going to just put this here. I don't think this is. Yeah, this is something that this is the example that I came up with. It's kind of artificial. I might want to do something like this. It doesn't compile, and I think it should be able to compile if that's what I wanted to do. But anyway, so the conclusion. Wait for the curtain to open. Okay. Part 4. Takeaways. So noexcept was invented to solve a problem that occurred because a contract promised too much. I think so. Noexcept operator is typically used to move and swap operations. That's about it. And what happened here?
You're at the end of your slides.
Did it just die? I guess I just ran out of power. That's good timing. That's wild. The noexcept specifier is used to decorate move and swap operations, and that's about it. And it's effective for algorithmic optimizations. Anyway, yes?
What is the contract that you mean that promised too much and led to noexcept?
Okay, so the question is, why don't I just get to this, and I'll answer that question after. Okay, so these are I'm going to just put this up. These are the reasons that you might. These are the reasons you might want to read the book. And now I'm going to answer the question: what did I mean about a contract where noexcept is promising too much? So the answer to that question is, suppose I say, well, if you call the bracket operator in contract, it will never throw, right? So I say does not throw, right?
Sorry, in your slide, you refer to one particular contract that promised too much, and that's what led to noexcept.
Oh, the one particular contract that promised too much was for pushback, in place back, or insert at the last element. The standard gives you the strong guarantee. And because of that, you can't do one optimization. You have to do something that's a little bit of a pessimization on the best possible. When you can move, you can skip one of those copies. Do you remember when we were doing it and I said you can skip a copy?
I just wanted to make sure. It is pushback or
Pushback or any of its friends. Yeah. So as I said, these are some reasons. This is on the back of the book. And obviously, I'd love you to look at the book, and I'm going to hold up the book because that's what I do. Here is the book. It's finally done. It is huge. It's a big book, but there's a lot of good information in there. So I do encourage you, if you're not as familiar with 11 and 14, most of you probably are very familiar with 11 and 14, but if you're not as familiar with 11 and 14 as you are with 98 and 03, then that book was written for you, the older generation, so to speak. It was written for me, was written for some of the people who have been moved up at Bloomberg, who are now senior managers, were very good designers in their day, but they don't code day to day, and they aren't familiar with all of the things that have happened to C++ since then they became in the management chain. So not surprising. Anyway, I still have 1 minute and 25 seconds. Any more questions? Well, then I want to thank you for coming, and I actually made it through one of my talks without using the last 10 seconds. Thank you so much.